So this problem involves a sewage treatment plant. We have a certain amount of waste water that comes into the plant as a function of time. We're given the rate that it's coming in. We know the rate that it's going out, in this case the rate that it's leaving, this L of t. It's a constant function of time. And we're told that initially the plant is empty. Namely, at time t equals 0, the volume of wastewater inside the plant is 0 gallons. Now it's important right from the beginning that we understand that E of t itself is a rate. It's basically dV dt, the rate that the volume of sewage is increasing as it flows in. This L of t, again a constant, is the rate dV dt that the volume is decreasing as it flows out. We have to keep in mind that relationship between the fundamental quantity here, which is volume of waste inside the treatment plant, and the fact that what we're given are the rates that volume is being increased because of incoming waste and being decreased because of outgoing treated waste. So A is asking us about how much wastewater enters the treatment tank. Well, to find the volume, we simply have to integrate the rate that the wastewater is flowing in over the period of time in question. And so once we interpret A properly, then this is a fairly straightforward part of the question. Notice it does not ask how many gallons of wastewater are in the plant after 4 hours, just how much comes in. And so we're just integrating from 0 to 4 the rate that it is coming in with respect to time. And we can evaluate this in a numerical approximation using our calculators. And we get 3981.02246. The question asks for rounded to the nearest gallon, and so that's 3,981 gallons. Let's go on to B. Now, when is the amount in the tank the greatest? Well, when we hear greatest, we're being asked for a global maximum. That's a global max. Again, it's important to remember that the quantity in question is the volume, not the E or the L, which are rates of change of the volume. We're interested in the global max of the volume. Well, we know where to look for global maxes. Either we look at the endpoints, and those are 0 and 4, or we look at the place where the derivative dV dt changes from plus to minus. Now, what is dV dt? Well, there it's important to understand that dV dt is E of t minus L of t, the rate that water is flowing in minus the rate that it's leaving. So what we're really asking is, when is E of t minus L of t changing from positive to negative? Let's first go with the endpoints. At 0, we know how much sewage is in the treatment plant tank, and that is 0. When it's at 4, meaning time equals 4 hours, we know there are 3981 gallons. So those are two possible candidates for the global maximum. Now we look for places where E of t minus L of t changes from positive to negative. Well, again, L of t is 645, and so we can numerically evaluate. We can graph E of t minus 645, and when we graph it numerically, we see that this condition is met at t equals 2.30934. Now, it changes sign from negative to positive at 3.559 hours. But we have to reject that because that's a potential local min, not a local max. So we now need to see how much wastewater is in the tank at 2.30934 hours. And that is going to be V of t is going to equal the integral from 0 to, let's see, t equals 2.30934. Be the integral from 0 to 2.30934 of E of t minus L of t, plus how much there is in the tank at the start of this interval, namely 0 gallons. So we can evaluate that numerically. And we get an approximate answer of let's see, we get an answer of 1,600, about 1,637 gallons. So those are all the places we have to look for global maxima, or rather for local maxima. And then from among these three choices, we now see that it's the 3,981 gallons that is the point where we have the most wastewater in the tank. But it's important that we tested the initial endpoint as well as the internal local max. Okay, so what does C now ask? What would it cost to treat the effluent? Well, for each bit of effluent that we treat, there's a price that we pay, and that is 0.15 minus 0.02 T. Now notice the price that we pay to treat depends on the time. If it weren't a function of the time, we could just find out the total amount of effluent that flowed in, namely the 3,981 gallons, and multiply it by the cost that it is to treat each gallon. But the fact that the cost for treatment changes as a function of time, cost per gallon, I guess that's the treatment cost. The fact that it changes as a function of time forces us to handle this as an integral. And so we must integrate E of t, how much is flowing in at any given instant, times C of t, let's call this C of t, cost as a function of time. And so it's the product of those two things that we have to integrate from 0 to 4. We can evaluate that, of course, numerically. And we get an answer of 474.31974. And so what we're really saying is, rounded to the nearest dollar, $474.